Welcome to the fourth and final section of the Introduction to FLAC3D training. So we've done so far using the user interface, some basics of grid generation, and some more details about using the sketch tool, how to use the model pane. And now we get to the real meat and potatoes here, which is how to actually solve the model and do the interpretation. So from now on, we've done pretty much everything we can do interactively when it comes to model building. And the rest of this is about using commands. Obviously doing the plotting and visualization is interactive, but the rest of the model solving part is going to be using commands. So here's where we start with making data files. So I can break out of PowerPoint. We can go back to our FLAC3D model. So hopefully you still have this open. If not, you can just open that project again and recall that we were playing with the model pane and we densified these regions around the tunnel. And we also gave group names to the faces we will use in about 3 minutes. So what we need to do next is create a new data file. So we can go up here and say new data file, and let's call it initial. It appears over here in the project, and we have a blank data file here. We start typing. We can start by restoring the state that we've just saved. This is always not a bad idea to do so that you can figure out where you are in the model. So I can say model restore geometry 2. And again, if I don't give an extension, it will assume that I mean .save. If I don't start by restoring this and I run this multiple times, weird things will happen because it'll keep on building things on top of things without starting fresh from the existing state. So it's a good idea to either put a model new at the beginning or a model restore at the beginning. So I'm restoring this state that we already created with the sketch and the model pane. Now recall when we were looking at the model pane, I was telling you how we have these hanging nodes where there's a node that's disconnected from any other nodes here. It's just like butting up against this face. You can deal with that, but we need a special command. And the command is this: zone attach by face. Okay, so I'm looking at the state record down here. Let's go back to the console so I can get information about things that I'm doing. So if I just run this data file, zone attached by face, it takes a few seconds here. It says it found 11,086 faces and it attached 2,809 grid points. So there's 2,809 of these dangling grid points that it is attaching to the opposing face so that we don't have a sort of a discontinuity in stress or displacement. If you forget to do this, it will be quickly obvious when you run the model because you will see all these stress concentrations or discontinuities or whatever, where these zones are discontinuous, where the grid points are not attached to the faces. So you will pretty quickly realize that something bad has happened. Whenever you do this densify, just remember, whenever you do this densify, you want to use the zone attached by face before you do anything else. So we start with zone attached by face. And here I can even leave myself a comment. So we haven't talked about it yet, but if I want to leave a comment in a data file, I just use a semicolon. So I can say, this is necessary when using densify. Okay, so it's handy to leave yourself comments. I do it all the time. You can even comment large sections of this data file. So imagine you had like 10 lines or something that you wanted to comment and you didn't want to go down and type a semicolon in front of them all. You can just select them. And there's a little thing over here, which is a picture of a semicolon, and comment all the lines. I could go back here and then uncomment all the lines. So this is sometimes useful. Okay. So next part, assign constitutive model and properties. Now recall, we could have done this in the model. Oh, hell, I didn't record. Did I hit record? Yes. We could have done this in the model pane. We can just click on different regions and assign different constitutive models and different properties. In this simple model, it's just as easy to actually type it in here. So zone, C model, 9, more Coulomb. So there are many, many different types of constitutive models that are included with FLAC3D. In this case, we'll just use the simple more Coulomb that almost everyone's familiar with. We have a whole training video on different constitutive models, which you can watch later on if you want to. For the more Coulomb constitutive model, we need some properties. So zone, you need some stiffness properties, which could be Young's modulus and Poisson's ratio. Those are probably the most commonly used things. In this example, we're using bulk modulus, shear modulus. Again, you can use Young's modulus and Poisson's ratio, or you can use bulk modulus and shear modulus. Either one of those things will work. You'll see a lot of examples in the manual that use bulk and shear. Probably in real life projects, you're mostly using Young's modulus and Poisson's ratio. In this case, we also need to give a density. This density is lower than the real density of rock. This model is somewhat contrived just to create interesting results. So for now, we'll just say density 1000. Note that I did not say anything here about what units I'm using. Okay. FLAC3D does not actually care about what units you're using as long as you're consistent. And so there's a whole discussion about this in the help. So if I go to, well, actually, let's just do it this way. If I go to help and documentation, let's open it in the default browser. In here under Itasca software guide, underpinnings, system of units, there's a discussion here about how Itasca software accepts any consistent set of engineering units. So unlike other programs, I don't have to specify in advance which units I'm using. I just have to be consistent. And so commonly, you will use meters and pascals for stress, which is fine. And then your density is kilograms per meter cubed, and your forces in newtons, and so on. In civil engineering, it's often common to use kilopascals, also fine. In mining engineering, when you're dealing with rocks, it's often common to use megapascals, also fine. You just have to be careful about your density. So if you're using kilopascals, you need to take your density in kilograms per meter cubed and divide by 1000. And if you're using stress in megapascals, you take your density in kilograms per meter cubed and divide by 1,000,000. Everything else is straightforward. It's still meters. And gravity is still meters per second squared. So it's relatively easy. Imperial units, often in the US, we're using imperial units. Feet is relatively common. Then your stress units are pounds per square foot, and so on. It's theoretically possible to use inches. I've never actually seen anybody do that. For the scale of the models that we're doing in geomechanics, that starts to get pretty weird. But certainly, and I've also never seen anyone do centimeters, but these three are very common. This one is quite common. Just make sure that you're consistent. Okay, so in this case, I'm just using pascals, and it's often not a bad idea to leave yourself a note. Units are pascals, so when you come back to it later, you can figure out what you were doing. Okay, so I've got bulk modulus, shear modulus, density. I also need to specify cohesion, 3, tension strength, 2 E3, and a friction. You can also specify a dilation angle. If you don't specify anything, it defaults to 0. Okay, so I'm whipping off these commands here. obviously, if you're not a FLAC3D user, you don't know where these are coming from. So there's a couple of ways to figure it out. Let's pretend maybe you know to assign a constitutive model, its zone C model assign, but you just don't know what this constitutive model is actually called. So I can go here and click F1 to get to the correct section of the help. Right, so it opens up here on the side, zone C model assign. This is the section of the help model that relates to this command. And it tells me here which constitutive models I can assign. So anisotropic, elastic, orthotropic, these are alphabetical. So down here somewhere is more Coulomb, and so on. And there's also a link that tells you all about the more Coulomb model if you wanted to go and read about how that works. Similarly with zone property, I don't necessarily know what these zone properties are. So let's hit F1 here and see what happens. Right, so here, zone property, I'm in the help, and here's all the different material models. Each different material model has its own properties. So I would need to go down here and look for more Coulomb and click on the link for properties, and then it tells me all the different properties I can specify. So that's one way to do it. Another way to do it, so this is getting to the actual help. Another way to do it is we have this sort of IntelliSense with the data files, which sort of intelligently will complete commands for you, or at least allow you to choose how to complete commands. So for example, let's pretend you didn't know anything. Just know that I wanted to act on zones. Note that in version 7 and above, all the commands start with the thing that you're acting on. So it's zone something, zone face something, structural beam something, zone grid point something. So it's always the thing that you're acting on that you start with. You know, if you were in PFC, you would say ball something. If you're in 3DEC, you say block something. So let's pretend you don't know anything. You just know that I'm want to do something to the zones. I can start typing zone and then hit Control Space. So I can either hit, it tells you down here at the bottom, Control Space for inline help, or F1 for help. I can hit Control Space, or I can hit this little arrow here at the end. Does the same thing. I hit Control Space. Here it tells me all the things I can do to zones, right? Zone apply, zone attach, which I just did. Zone create, we talked about before, and so on. So I got zone already, and now I want to do the C model. So I can right-click on that and say Insert Selection. So I've got Zone C model. Now I want to assign something here, so I can right-click on that and say Insert Selection. And then I want to choose one of these models, so more Coulomb. I can right-click on that and say Insert Selection. So you can see how you can build up these commands without ever actually typing anything. Maybe just typing the first word to get started. Same with the properties. Zone. Let's do it again. Control Space. Let's go to property. Well, again, the properties are broken down by the different type of constitutive models. So I know that I'm using more Coulomb. I can drill down here and say, oh yeah, bulk, insert selection. I need to give a number here. So whatever it was, 3E8. And then I need a shear. I can insert that selection and give whatever that was, 1E8, and so on. So you see how you can build up these commands by using this inline help. You can also just hit F1 on any one of these things as well, and it will open the section of the manual over here. Okay, so let's get rid of this. So that's just a little bit about how you can make your life easier when it comes to typing in commands. So far, we've restored the geometry, we've attached by face, we've given it a constitutive model, we've given it some properties. Need to assign some boundary conditions. Okay, now it comes in handy where we were messing around in the model pane and assigning group names to the faces, because we want to apply boundary conditions to the faces. So again, the commands start with the thing that is being acted upon. So zone face, apply, what I can do is say velocity normal. Because remember, we made this slightly crazy model. You know, often you can just say fix the velocity in the x direction or fix the velocity in the y direction, and it puts roller boundaries on here. Remember, in this case, we extruded it, and then we aligned the boundary with the perpendicular to the extrusion direction. So this doesn't necessarily line up with x or y. But luckily, we have this command that says velocity normal. So we'll just put a roller boundary on there and prevent it from moving normal to the face. So I can say zone face apply velocity normal, 0. So I want to have 0 velocity on those faces. Range, group. And now we can use those group names that the model pane came up with. So west, right? And then I could theoretically copy and paste this line and say range group east, and so on. That ends up being a lot of typing. I can make this a little bit simpler by saying range group west, or east, or north, or south, or bottom. I don't want to fix the top because it's the actual surface of the Earth, but I do want to fix all of the other things in the normal direction. Now, note how I've got a really long line here, which is kind of annoying, especially when I'm doing a training course because you can't see it all. You can have a command that extends over 2 lines or more. And so all you need to do is add 3 dots here and hit enter, and it will continue on the next line. You don't have to add spaces here, but I always do just to make it clear that this is part of the same command. It also puts a little and symbol here on the column to indicate that this is all part of the same command. So even though this is on 2 lines, it will interpret it as one single command because I have these 3 dots here. Okay, so this is boundary conditions. Again, I can leave myself a comment. Maybe now I want to double check that I've done this correctly. So I can run this thing, just hit the green arrow. Doing the attach, it's assigning the properties. It says it's applied conditions to 5,192 grid points. So I'm feeling pretty good about this, but maybe I just want to double check. So what I need to do now is make a new plot. So I go new, and I say plot. We've seen this before. Let's call it zones. And as we did before, you can just use this dropdown to show the zones. And as before, it defaults to showing the groups. This looks very similar to the model pane. Okay, so you're probably asking yourself, why am I making another plot? Why not just go back to the model pane? First of all, the model pane does not have the ability to plot all the different types of things we're going to plot here. It really only just plots the zones and the faces. Secondly, the model pane is specifically designed for you to be able to interact with it, to be able to change group names, change constitutive models, change properties, and so on. When you make a plot, you can't do anything. You can't change the state of the model. You can plot things, and you can hide things in the plot, but it won't actually change the state of the model like the model pane does. And so the distinction is important. We want to be able to create these plots and not mess up the model. Anything that messes up with the model is restricted to just the model pane. Otherwise, it gets super confusing because you have 10 plots open and you change one of them and it changes the model and then it breaks all the other plots and you've got a mess, right? So think of the model pane as a special plot that's interactive. Okay, so this shows the groups. We could change it to show the face groups. Right, so there's the face groups that model pane came up with. We can add to this plot the boundary conditions to make sure we've done it correctly. So if we go up here to the plus, actually it's called GP fixity. So if I double click on that, lots of these little lines that show me where the grid points are fixed. So the blue lines are fixed in local X, the green lines are fixed in local Y, the red lines are fixed in local z. So you can see that everything on the boundary here, except for the surface, is fixed in the perpendicular direction, which is exactly what we wanted. So now I'm happy with this. I don't need to see this anymore. I can just hide this plot item by clicking on this little circle, and that just hides it. While we're in this plot, we can talk a little bit more about plotting. We showed the basic plotting before. There are lots of other things you can do here. So I quickly showed here how you could change the label from groups to face groups. So it defaulted to group. I can change it to face group. I could change it to constitutive model. So I change it to model, right? It's telling me everything is more Coulomb. There are other things I can do here. When we get to something that's been solved, we can change it from label to contour and look at things like displacements. So far, they're all 0, so that's not interesting. So let's go back to label. Again, we've already talked about how you can spin it around and zoom in and out and things like that. If we change this back to group, you can do things like we did in the model pane. I can right-click on this guy here and say, hide this group. And this group has 3 different names, right? Its block is block 19, its segment is segment 1, or it could be both. If I choose the both, it just hides this guy here. And I do that, what it's doing behind the scenes is making a range for this plot item, right? So here's my zone group plot item. If I expand it outwards, I can see cutting to a clip box. I'll talk about that in a minute. But there's also this concept of range. If I expand that out, you'll see that it's created a range called group. If I click on that, right, it's telling me that it's not plotting group block equals block 19 and block equals segment 1. So I can make up all kinds of crazy complicated ranges here for my plot. Oops. Now it's not plotting anything here. If I just click this circle next to the range, I'll show everything again, and it ignores the ranges. I can right-click on this group range and get rid of it and hit delete. But I could theoretically go here and add different ranges, very similar to what we did in the model pane. So if I go into here and I say add range element, and say position X, for example, this is almost exactly the same thing we were doing in the model pane. The only difference here is that it defaults to not. So I can do this interactively, same way we did before, and just drag these things here. And you can see the part that is within the range is solid color, and the part that is being excluded is the transparent color. If I just want to choose this middle bit, I can uncheck the not, and I will only plot this middle bit, right? So I go back and click on zone group. This range is saying that only plot the things that have a position between, an X coordinate between 12.4 and 80.3, right? And again, I could type in numbers here by hand, but I can also do it interactively. So this is all about the plotting, right? Just to be able to dig down and look inside the plot. Exactly the same thing we were doing in the model pane. So you can have a bunch of different ranges here. You can do different things. For now, let's just get rid of that. The other thing you can do that's very common in these 3D models is to have a cutting plane, because often you want to see what's happening inside this thing. So here's the cutting tool. If I click on the cutting tool, by default, it will make a cutting plane perpendicular to my eyes viewing this model, right? So let's put the axes on here quickly. So here's my axes. If I reset the view, remember this button here resets the view, or I can use Control R. It goes to the XZ plane. So now if I make a cutting tool, it's going to make a cutting plane in the XZ plane, right? And so now I'm looking inside of the model. If you spin it around, you can see that I've only got a little plane here. I click on cutting tool, I can see what I've got here. So the Normal to the plane is 0, 1, 0. So it's the normal is in the y direction. The origin is this coordinates here. I could change these by hand. I can also move the plane up and down by using these arrows, which is super useful. So if I want to move through the model, right, I can just click these arrows and sort of gradually march my way through the model, and the cutting plane changes, or the cutting plane origin changes, right? I could also set it so that it only plots the zones in front of the cutting plane. This is sometimes useful, right? So now let's march through it. You can see I'm only showing part of the model here. I could also change or just choose the ones on the back or whatever. I can make this more complicated. Instead of just being a plane, I could make it an octant or a wedge. So let's pretend I've got a wedge here. So now I'm just plotting a wedgy bit of this model. Instead of front, let's choose back. So now I'm excluding a wedge of this model. It helps me look inside of it. So this is kind of a useful thing. You know, if I want to look inside of this thing. Probably the most common use is just the cutting tool plane. Now, just a couple other things to say about this plot. Let's get rid of this cutting tool. Let's pretend I've zoomed in. Maybe I've got a bunch of cutting tools or a bunch of ranges, and I've spent some time making this plot quite complicated. And I want to save this particular view. So what I can do is I can go here to the plot views and controls. This is another control item here. So here it's telling me what the exact view is. I can do here is give it a name. So I can hit plus and call it my view. Okay. And so now I can spin this around and mess around with it some more. You know, maybe I want to check something else out. And then I was like, okay, I would like to get back to that view I was just looking at. I can go to this drop down and go back to my view, and it goes back to the view that I was just looking at. So this is a potentially useful thing. Also, while I'm here, some other useful things is, remember I said that the reset plot button goes to the XZ plane. You can choose other planes to look at. So you can go in the positive X direction. You can look in the negative X direction. You can look in the negative Z direction if you want to look top down, and so on. There are keyboard shortcuts for these things too. But if you can't remember, you just turn on these tools and you can choose these different views here. The positive Y direction is the default. Okay, that's all I'll say about the plots for now. We can come back to this when we're looking at the contours. Okay. So let's go back to our data file. We got the boundary conditions, we checked them out, we're happy with that. Most of the time in geomechanical engineering, you also want to apply initial conditions because you have some material that's been sitting there for a while and you've got gravity and have some stress in it already. So first thing, you can set it up to automatically calculate the stresses due to the weight of material. But before to do that, you need to give it you need to tell it what gravity is. So you say model gravity 9.81. It's certainly possible to run models without gravity on. Most of the time, probably you are turning gravity on. And most of the time, if you're using metric, the gravity is 9.81 meters per second squared. And also, most of the time, the gravity is acting in the negative Z direction. So the gravity is pointing down. If for some reason you had a model where the gravity is not pointing down, you can be more specific and give a whole vector here. So you could say, you know, let's say it was a centrifuge test and maybe the gravity is acting in the X direction. You could say minus 9.81 in the X direction, 0 in the Y direction, or 0 in the Z direction. It's rare, but it's possible. If you want it to act in the negative Z direction, you just specify the gravity. Okay. And then there's a super handy command called zone initialize stresses. And this will work out the stresses automatically based on the density of the material and the gravity. Okay. There are other keywords associated with this. So if I go and hit the help, I can give ratios, right? So by default, it will set the vertical stress based on the gravity. It will set the horizontal stresses equal to the vertical stresses. Often that's not what you want. You can specify these K0x and K0y ratios by giving another keyword like this ratio 0.5, 0.5. This will specify the X component of initial stress to be half of the Z component of initial stress. Often that's what happens in civil engineering problems. Sometimes in mining problems, the ratio might actually be more than 1. You might have a higher horizontal stress than vertical. In this case, we'll just assume it's 1 to 1. Okay. I can leave myself a comment here. Initial conditions. It's sometimes useful to take a history. For now, we'll just take one history. We'll do another one later and do this model history, mechanical convergence. And I'll explain what this means in a minute. But let's just get to the solving. Last thing we need to do is solve it. Before we solve it, we need to tell it if we're running large strain or small strain. In version 7 and before, it just defaulted to small strain, and you never had to say anything about it. In version 9 and above, you need to specify if it's large strain or small strain. So most of the time, here, this is solving. Most of the time, you're turning off the large strain, unless you have very large slope movements or run out or something like that. In geological engineering, we're usually talking about mostly small strain type problems. So I can say model large strain off. If you want to read more about large strain and small strain, you can look in the manual. For now, I will just say that most of the time we're turning off the large strain and running in small strain. And then I can say model solve. So a lot of the examples will just use model solve. And if you've used FLAC3D before, you will probably have seen this model solve. And this is fine. This will work. The more rigorous and accurate way to do this is to say model solve convergence 1. And I'll explain that in a minute. And then I'll say model save initial. So let's run it. We'll look at it, and then I'll just talk a little bit about what's happening with this solve. So we can run this whole thing from the beginning. Attaching the faces, assigning the boundary conditions, and then running to solve. It solved quite quickly, which makes sense because we specified an initial stress, we specified the correct boundary conditions, everything should be approximately balanced. It should solve quite quickly. Now, what does solve actually mean? If you watch the very first video, the sort of general numerical modeling video, we will have talked about this already. But since we're in the middle of an actual example here, we'll just talk about it a little bit more. So I'll go back to the PowerPoint for a minute. Okay, convergence. When all forces acting on a grid point sum to 0, that grid point can be considered in equilibrium. Okay. The sum is never actually 0. It gets close to 0, but there's always a little bit of vibration and slight unbalances and so on. So we need to sort of decide when this thing is at equilibrium. When do we consider it to be solved? When do we consider it to be balanced? The terminology for that is the convergence criteria. So if I had just typed in model solve, which again is very common, and you'll see it in a lot of examples and a lot of old models, it uses the default convergence criteria, and that is a ratio of 1e minus 5. And what that means is this is a ratio of the unbalanced force to the applied forces. And again, if you need the details, you can go back to that very first presentation about sort of the generalities of numerical modeling and the explicit method. But imagine you start out with a very large applied force, and you also have a very large unbalanced force, because you're applying a force and there's no stresses have built up yet, and it's basically not being balanced, then you're going to have a ratio of 1, right? The applied force to the unbalanced force is basically 1. As time goes by, the applied force doesn't change, right? So you're still applying the same force, but you're building up stress in the zones that are counteracting that force, that are balancing it. And so the ratio of unbalanced to applied force starts getting smaller and smaller and smaller, until eventually you get to some small number, and by default that small number is 1e minus 5, and then it says I'm solved, right? That's fine. People do this all the time. It works. The problem is that this is a global measure. It's the average in the whole model, right? So it looks at the average unbalanced force in the whole model and the applied force in the whole model, and it works out that ratio. And if it's below 1e minus 5, it says I'm solved. The problem is that you often have maybe little small parts of the model that are still not solved. But because on average the whole model is solved, it stops running. So the slightly more accurate way to do it is to use this convergence. So instead of this being a global criterion, it's more local. So now it says it looks at the ratio of unbalanced forces on any grid point. And so it does it grid point by grid point instead of, in a global sense. And so instead of specifying this ratio of like 1e minus 5 or 1e minus 4 or whatever, you just specify a convergence criteria of 1, which basically means that all the grid points are below the necessary unbalanced force. So again, without going into too much detail, you can go back and look at that initial presentation, but just be aware that this convergence criteria is a little bit more accurate, especially in models where you have a large range in zone sizes, or a very large model with a small detailed region or something like that, because this makes sure that every grid point is solved rather than the whole model in a global sense on average is solved. So just for fun, we could run this thing. You can say model history mechanical ratio, and you can just say model solve, and it will use that default ratio and try to get to 1e minus 5. So if we run that, just run this. Actually, that's solved quite quickly. See, this is a less stringent convergence criterion. It solves more quickly. We can look at this history. So let's go. We can make a new plot. That history. And one of these commonly chosen plot items here is a history chart, so that we can choose that. We've only got one history, which is this mechanical ratio limit. You can see it starts out at a relatively high number and then drops down to something below 1e minus 5, and that's when it stops. When I said before that it'll start at a very high number, there's two reasons why we don't see this being much higher at the beginning. Number one, the model is quite balanced to start with, because remember, we applied initial stresses that are balancing the boundary conditions, and so it's actually pretty close to being converged right from the start. Number two, it only takes a history recording every 10 steps by default. So in the first 10 steps, it probably reduced its solve ratio quite a lot. And we're only seeing the value here after 10 steps, and then 20, and then 30, and then 40. So this is only 4 points on this curve here. But you can see how it goes from some high value down to the 1e minus 5 number. If we run this again, instead of saying mechanical ratio, we take a history of mechanical convergence. We say model solve convergence 1. This is a slightly more accurate and stringent convergence criterion. So now it's done 135 cycles. If we go and look at the history, now instead of going down to 1e minus 5, it's trying to get to 1, right? And so this axis is times 10. So it starts out at 28, and then it reduces, and then eventually gets down to something that's 1. And then it says I'm solved. And you can see it here as well in the console. The convergence, we just run it one more time. Right? You can see the convergence here is some high number and it gets smaller and smaller. It goes quite quickly on my computer, but you can basically see what's happening. So great. Now we're happy. Everything's more or less balanced. We can assume that this is okay. We can, just for fun, go and look at our plot, our zone plot. Change the label to contour. By default, it shows displacements. You can see some very, very small displacements here, 2 e minus 5. So it moved hardly at all. It came to equilibrium. Everybody's happy. Cool. Now it's time to excavate something. So let's make a new data file. New data file. Let's call it slope. Again, we'll start by restoring the previous state. So model restore initial. And I'll leave myself a comment here. Excavate top bench. So here is where it comes in useful, the fact that we identified these different benches with group names in the sketch. Because what I could do is say, let me just type this first and then I'll explain what I'm doing. Zone relax, excavate, range, group, bench 1. And then solve, model solve, convergence 1. Okay? If you're an old FLAC3D user, you would not have seen this before. This zone relax command is relatively new. And what it does is it gradually excavates that bench. So I could have done this. I could have said zone, delete, range, group, bench 1. It doesn't matter here if I use capital letters or small letters. This is case insensitive. But I could have said this, zone, delete, range, group, bench 1. And then solved it. We'll try that in a minute just to see what happens. But first we'll do it this way. And what it actually does is it takes the material that makes up bench 1 and gradually reduces its density and its stiffness so that it's kind of acting as if it was being gradually excavated. To be super accurate about this, what we would actually do is excavate it gradually, bit by bit, using different ranges and so on. Maybe we don't want to spend that much time. Maybe we don't care that much about the accuracy. We can sort of simulate the gradual excavation by using the zone relax command. And so what it does is it reduces the modulus and the density, then solves, then reduces the modulus and density some more, and then solves, then reduces the modulus and density some more, and then solves, and so on, until that bench is completely gone. And I'll explain why that's something you might actually want to do in a minute. First of all, let's just watch it. So we can actually watch the plot as it's going here. So see here, we can see displacements. So that bench is gone. It solved itself. We've got some displacements. It turns out that these are probably upward displacements because we're removing that weight of material. So if I go to this plot item list and go to plus and add vectors, by default, the vectors are showing displacement. And if you look closely here, you can see that they're all mostly upward pointing. So what happened is we removed this material and then everything sort of rebounded upwards, right? That's fine. It works okay. Now, what happens if we just did zone delete instead? The problem with that is that because this is an explicit program, and it's solving everything kind of pseudo-dynamically, you have a huge force change right at the surface, okay? You've deleted all this material. You've got essentially a huge applied force at that surface. It's not balanced anymore. And what you get is this sort of dynamic wave propagating through the system, right? So you essentially get this huge force change. It's like a big pulse. And because this is a more Coulomb material that has some strength associated with it, it's possible that that pulse, the peak of that pulse, is enough to cause failure in the system. And that's not realistic. Obviously, you do not excavate, a huge 200-meter bench in like instantaneously and set up a dynamic wave. We do not want to see those dynamic effects here. So That's why we use the zone relax. We could do the zone delete just for fun and see what happens. We can go and look at the zones. Okay, that actually worked, but in some cases, what you will find is that you will get a lot of extra failure. In fact, we can just investigate that. So let's hide these vectors. And on this displacement plot, let's change it to label. Let's change the label to state. So this shows the failure state of the zones. These little P's indicate that something happened in the past, and the little N's indicate that something is happening now. This is a perfectly plastic, more coolant material. So what will happen is that the stresses will go up and hit the envelope, and there might be failure. The stresses will be redistributed, and then the stresses will reduce, and so it's no longer failing, right? It will go back to being elastic. So all these things that failed in the past, maybe we don't care about that much. And in fact, you can go over to the plot item attributes and check this box for no past. And it'll show you only the zones that are failing now, which is very few, which makes sense because this thing solved, it came to equilibrium. This slope is not failing. There are definitely some zones that may have hit that failure envelope, caused stress redistribution, that they're not failing anymore. So this is what it looks like with that zone delete. Let's just for fun try it with the zone relax and see what happens. Zone player. Okay, I mean, there's oh, this is the, so if I check the box for no pass, now nothing is failing. And if I show everything, there's probably less failure than there was in the case where we just deleted everything in one shot. The differences aren't that extreme in this case, but there's definitely cases in some models where if I just delete it all in one shot, I'm going to see a lot of extra failure that is not realistic. Okay, so the point of all that is we're going to use the zone relax command. So that was bench 1. We can do the same thing for bench 2. I can just copy and paste this. Again, if I don't want to run the whole model over again, I can just select these 2 lines and just run that part. Go back to my plot. I can see more failure happening here. Obviously, this is a steeper slope. I've removed more material. But again, at the end, almost nothing is failing currently. It's all failed in the past. I can go back and look at my displacements. I can add my vectors back on again. I can see maybe some slightly more worrying behavior here. You still get this uplift at the bottom, but now there's some shearing type of behavior up here. So yeah, maybe this model was intentionally designed to be pretty close to failure. So if it was just a little bit weaker, this thing would probably actually start failing. Okay, that's the slope excavation. Well, we can just save it, model save slope. Let's just run that line there. This is quite a long video. We are getting close to the end. Now we are just going to excavate that tunnel. So this follows more or less the same procedure. Let's save this data file. Let's make a new data file. Let's call it tunnel. Model restore slope. The font a bit bigger here. Now, one thing that we can do, and it is super useful, is we can reset the displacements. Because we have all this movement because of this slope excavation, maybe we don't care about that. Maybe this whole part of the exercise was just to get to the point where we're looking at the tunnel. Maybe these slopes have been there for 50 years, and we really just want to see what the problem is when we excavate the tunnel. So we don't care about those displacements. And if we excavate the tunnel, we're not going to be able to see really what's happening because they'll be swamped by the displacements that have already occurred. So we can reset. We can say zone, grid point, any displacement 0, 0, 0. Right? So it's going to take the X, Y, and Z components of displacement, set them to 0. So now we're just going to see the delta. Whatever happens when we excavate the tunnel is what we will see in terms of displacement. So I can see zone, it's exactly the same thing we did before, zone relax, but with one extra little trick. Now, this is a slightly tricky part. Because remember when we were assigning group names, let's go back to the model pane. Right? There's a group name called tunnel in the construction, which is this pink line. And there's a group name called tunnel in the segment, which is this red line. So if I just say range group tunnel, it's going to excavate all of this red stuff and all of that pink stuff, which is not what we want. We want the intersection of the red line and the green line. We just want that tunnel going through here. And so we need to be a little bit careful about how we identify the groups. So you could say zone relax, excavate, range, group. And this is the fastest way to do it. Construction equals tunnel and extrusion tunnel. So it's only going to excavate if it meets both of these criteria. So that should be equals. The groups are called tunnel in slot construction, and they're also called tunnel in slot extrusion. Okay. Now, just for fun, let's also make a history of the displacement at a point on the roof of the tunnel. All right, so we can say zone history. Let's say it's the vertical displacement. So disp z, and we give a position where we want to record that displacement. I don't know off the top of my head what that position is. So I go back to my plot. Well, I can go to the model pane. That might be easier. Let's go to the plot. I go to my zone plot. Let's get rid of these vectors. Let's change this back to groups. All right. I can figure out that the tunnel is actually this little bit here. And so what I want to do is take a history of displacement at a point on the roof of the tunnel. I can hang my mouse over here, and you can see the information box down here on the right tells me information about where my mouse is. So it's telling me the nearest grid point ID, the nearest zone, and also the location of this point. Now, what I really want to do is copy and paste that location. And I can't do that because as soon as I move over here, it changes, right? There's two things I can do. Number one is I can use this query. So we haven't talked about this yet, but this is totally useful. If I click on this little arrow with the question mark, I can select different things and get detailed information about those things. So if I click here near the roof of the tunnel, I can find out information about the zone, information about the face, or what I really want is what is information about this grid point. So I choose this grid point, tells me its position, its displacement, its velocity, and so on. I can just copy the position and then paste it into my data file. And it will take a history of displacement at that point, which is essentially the grid point on the top of the tunnel. Another cool way to do this is, let's pretend I didn't want to go to the trouble of using the query. If I'm here in the information, I can hit, let's see, Control Q. What that does is it brings the information box up here instead of being down on the right-hand panel. So now I can move around and that information box follows me around, which is cool because maybe I don't want this exact grid point here. Maybe I want it a little bit above that. So I hang my mouse a little bit above that. still want to copy that location, but I kind of can't do it. So what I need to do is freeze that box so it stops moving around. And I hit Control C for copy. Now the box is frozen, and I can just copy that location there and paste it into my data file here. Note that that box is still there. I need to get rid of it. So I figured out a way to identify a point above the tunnel where I want to take a history and monitor that displacement. And then I'm done. I just say model solve convergence 1, model save excavating. Now let's see what happens. All right, I'm running this thing. Great, no problem. Except that there is a problem. This convergence is not getting smaller. If you look at this convergence, it's banging around something E3 and is not really getting smaller. If I go to my history, look at what's happening here. Here's the first solve, came to convergence. Here's the second solve, came to convergence. Here's excavating the tunnel. It is nowhere near 1. It is a total disaster. This thing is never solving. If I go and look at my plot, let's change it back to displacement. Look at my displacement. I'm up to 4 meters of displacement already here. This is a catastrophe. I can stop running it by just hitting the stop key here. Go to my zones. I can exaggerate this displacement to make it look even cooler. If I go to my plot item, there's a box here under the attributes called def_fac for deformation factor. If you hang your mouse over, it gives you some information about what that is. I can check that box and exaggerate the deformation by like 2 times or even 1 time. No, that doesn't work. 2 times. Right, so I can see what's happening here. This tunnel is basically collapsing into the hole. This does not solve, right? It will just keep on failing forever. Let's get rid of this deformation factor and let's plot the states. Right, so everything up here is failing shear now. Let's hide the past. Oh, look, a whole bunch of shearing now. It's a catastrophe. Yeah, this model is not solving. So what you would do in real life is if you weren't sure that this model was going to solve, you would set some sort of limit to the number of steps here, right? So I can say model solve convergence 1 or cycles 2000, right? So it's going to try and get to convergence 1, but if it does 2000 cycles and never gets there, then it's going to stop. And this is useful if you have a big model and you want to run it overnight and you don't want to sit here and watch it. You can just set something like this up and it will just automatically stop after 2000 cycles. So here it goes, it's still running, It's a disaster, it's not solving. There, it hit 2000 cycles and it stopped and saved. So there's my, let's put the displacements back on. Now, just for fun, we could change this so that it actually works. Oh, before we do that, let's look at the other history. So this is the convergence history disaster. Let's get rid of that one and let's plot the Z displacement history. You can see what's happening here. It starts out at 0 and then it gets more and more negative, and this thing is just collapsing. All right, just for fun, let's make it converge by increasing the strength. So if I say zone, prop, cohesion, 1E4, before I start solving, it will sort of instantaneously strengthen everything here. And we'll see if that actually solves. Yeah, you can see the convergence here is getting close to 1. So there it is. We can look at our history. Right, so we got a little blip at the beginning because we did this weird instantaneous strengthening of material. But then we get a big drop, and then it levels off. But the drop isn't that big. You can see here we're talking about millimeters. And then it flattens off and comes to equilibrium. So by strengthening this thing, it actually worked okay. Look, it's interesting. You can see more displacement in the middle here than on the edges. Okay, and that's pretty much the end of this. Just as one other interesting thing, I'll just talk about these history plots a little bit. You have a lot of control over what you're plotting here. So, for example, it defaults to plotting this light blue line. Most of the time, I like to change that color. So if I go into the attributes and I go into series, I can change that to say, oh, it opened off the screen, but I can choose the color and make it dark blue. I can make the line thicker, whatever I want. I can change the axis title. So axis 1, step is fine because that's what it is. Axis 2, I can make it something else. Let's make it displacement meters, right? I could change the exponent. So right now it's plotting times 10 to the minus 3. Just for fun, I could say, let's just make that not an exponent, not scientific notation, so that it plots it like this. Not so useful in this case, but is often useful in other models. Right, you can change the fonts and labels and marks and so on. So you do have quite a lot of control over these history plots. And again, with these plots, you can just right-click on it and say export as a bitmap, which is useful. With a history plot, you can also right-click on it and say export as a CSV file, and it will actually export the data, and you can bring it into Excel or whatever you like and have even more control over the plotting. So that's kind of a powerful thing that you can do. Okay, that concludes this tutorial and the introduction to FLAC3D section.